In Lesson 2, we'll learn about the arrow relation between near numbers. Any pair of real numbers are either equal or not equal, meaning that they either do or do not sit still at the same spot on the real line. In the context of near numbers, equality is not the right concept. Instead, for any two near numbers alpha and beta, we have the arrow relation, which either holds or doesn't hold. This symbol is best read as fits into, but sometimes we'll say goes to for brevity. The best analogy for the meaning of the arrow relation is a game of follow the leader, which will illustrate with the statement that 1 plus fits into 1 plus minus. The near number on the right, the leader, sets smaller and smaller targets, and the near number on the left, the chaser, has to be able to squeeze enough to stay inside those targets. This game of follow the leader continues forever. If the chaser can fit inside every target the leader paints, then the arrow relation holds. In terms of slices, for each slice of beta, in other words, whatever target it paints, there is some slice of alpha that fits inside it. Again, beta squeezes forever, and alpha must be able to squeeze enough to eventually fit inside every target slice painted by beta. There's only one other possibility, as is the case if we switch the roles of these near numbers. At some point, the leader paints some target that the chaser can't ever fit inside, no matter how much it squeezes. In terms of slices, there is some slice of beta that no slice of alpha fits into. In this case, we say that alpha does not fit into beta. Let's see that all again with a couple of basic infinite near numbers. The concept is identical. Positive infinity fits into positive negative infinity because whatever target positive negative infinity sets, positive infinity can squeeze far enough to fit inside. Positive negative infinity does not fit into positive infinity because positive infinity can set a target that positive negative infinity can never fit inside, no matter how far it squeezes. If alpha fits into beta, it's possible that beta fits into alpha as well. We indicate this with a double-headed arrow, which means that alpha and beta are effectively equivalent as near numbers. Note that we're avoiding the word equals. A quick review of our definitions. Alpha fits into beta means that for every slice of beta, there is some slice of alpha that fits inside. Alpha does not fit into beta means that there is some slice of beta that no slice of alpha fits inside. Comparing these two definitions, it should be clear that for any pair of near numbers alpha and beta, one and only one of these conditions holds. Either alpha can fit into every slice of beta, or there's some slice that it can't. Now let's think through a few more examples, this time not saying in advance which of these two things happens. Pause the video when the ellipsis comes up, and think them through yourself before continuing. Does 1 plus minus dot fit into 1.01 plus minus dot? The question is still pretty simple as long as we remember that both of these keep squeezing forever closer to their respective limits. At first it appears that we're in good shape. The leader squeezes, and the chaser can keep up. But remember that this must work for every slice of the leader. If we look closely, once we squeeze past a certain point, once the target slice squeezes away from 1, we see that the chaser 1 plus minus dot can never squeeze to fit inside that target. So 1 plus minus dot does not fit into 1.01 plus minus dot. This is an example of a general phenomenon. If a and b are distinct real numbers, none of the basic finite near numbers squeezing towards a fit into any of the basic finite numbers squeezing towards b by similar reasoning. Does this near number gamma pictured at the top fit into 0 plus minus dot? Note that gamma is a bit lopsided, but both sides squeeze forever closer to 0. Yes, this does meet the definition of the arrow relation. Speed doesn't matter as long as you get there eventually. Gamma can fit into every target painted by 0 plus minus dot. How about the other way around? Does 0 plus minus dot fit into this near number gamma? Again, speed isn't an issue as long as every target can be hit. No matter how far gamma squeezes, 0 plus minus dot can squeeze enough to fit inside. This pair gives us an example of two distinct but equivalent near numbers. Since gamma fits into 0 plus minus dot, and 0 plus minus dot fits into gamma, we have that gamma is equivalent to 0 plus minus dot. Does the constant interval 1000 infinity fit into positive infinity? They both look fairly similar, although the leader squeezes and the chaser doesn't. Well, the leader positive infinity starts out with numbers bigger than 1, then bigger than 10, bigger than 100, etc. If we're patient, we can easily find a slice of positive infinity that the chaser doesn't ever fit into, which is enough to see that the constant interval 1000 infinity does not fit into positive infinity. What if we reverse their roles? Does positive infinity fit into the constant interval 1000 to infinity? Yes, in this case, the game's pretty easy. Since the leader doesn't squeeze at all, there's just one target to hit. Can positive infinity squeeze enough to fit inside? Eventually, yes. The takeaway here is that we need to know exactly what it means for one near number to fit into, or to not fit into, another one. Given any two near numbers, you can think through the definition yourself. This ability to think it through is important. This isn't about memorizing rules, it's about understanding the concept and its definition. Now that we have the arrow relation in hand, we're ready to make a few definitions. A near number alpha converges if alpha fits into L plus minus dot for some real number L. In other words, if it squeezes nearer and nearer to some number. When we hear convergence, we should picture things like 0 minus, 5 plus minus, 2 plus minus dot, etc. Note that our target L plus minus dot is as inclusive as possible. If alpha squeezes to L in some more limited way, say alpha fits into L plus or alpha fits into L minus dot, then alpha still fits into L plus minus dot, so all of these count as convergence. If alpha fits into L plus minus dot, we call this real number L the limit of alpha. To be clear, this is a plain old real number. But always remember, when you see the word limit in calculus, there is actually some sort of squeezing going on, not just a number sitting still. A near number diverges if it doesn't converge. That is, for no real number L does it fit into L plus minus dot. In terms of our basic near numbers, all of the basic infinite near numbers diverge, as does any constant near number containing more than one point. For not one of these is there a single real number that it's squeezing toward. In fact, any near number that just fits into positive negative infinity, which includes the cases of fitting into just positive infinity or just negative infinity, must diverge. Because if we picture the targets it fits into, they prevent it from possibly squeezing towards any number. We should note something here. If a near number alpha fits into any basic finite near number, it converges. If it fits into any basic infinite near number, it diverges. What about fitting into a constant near number? That's our last topic to discuss. Let's consider one last question. What near numbers alpha satisfy the statement that alpha fits into the constant interval 0 infinity? Here's the target which doesn't squeeze. Not everything fits in. For example, negative 1 plus minus dot doesn't. And even 0 minus doesn't. But 0 plus does. So does 1/2 plus minus dot, and in fact, any other near number with a positive limit. Positive infinity fits in too, and as with any near number, the constant interval 0 infinity fits into itself. So, does this statement that alpha fits into the constant interval 0 infinity allow us to determine whether alpha converges or diverges? No. Some convergent near numbers fit into 0 infinity dot, as do some divergent ones. Because the statement that alpha fits into 0 infinity dot doesn't allow us to determine whether alpha converges or diverges, we call the statement indeterminate for alpha. The target that alpha fits into just doesn't give us enough information. To be clear, the near number 0 infinity dot diverges, but a near number that fits into it could converge or it could diverge, which is what makes the statement that alpha fits into 0 infinity dot indeterminate for alpha. This happens when the leader sets targets that are in some sense too wide open, allowing lots of different behaviors to fit inside. Now that we have our basic near numbers and the arrow relation, we'll next move on to discuss how functions and arithmetic work for near numbers, then we'll finish with formal proofs of near number statements. Please share this video and check our blog, where we'll announce new videos and discuss questions that come in. And don't hesitate to use the contact email below if you have any questions along the way.